everybody. I hope everyone's having a wonderful day. So, today we're going to be talking about AVL trees. So last day I introduced you to the idea or the big drawback of just general binary search trees. Where, remember, we showed all those major operations we were doing with binary search trees like get, put, remove. These all take big O of H, where H is the height. So I showed that there's kind of a continuum between having really nice balanced trees and these degenerate trees, ones that form basically a chain. So the height can vary between big O of log n to big O of n, where n is the number of nodes. So the idea that I proposed is that instead of having it where we just allow this mutation to occur in the tree, what we're going to do is we're going to perform what is called a self-balancing tree. So whenever we make modifications to the tree, we're going to make sure that it maintains a so-called height balanced property, which we're going to describe today. And that height balanced property, as I'm going to prove for you, will guarantee that the height is always going to be big O of log n. So that's going to be one of the big things we're going to talk about today. And then we're going to hopefully maybe have some time to talk a bit more about AVL trees beyond that. So I'm just going to remind you where we were last day. So I defined what the height of a node is. So a height of a node is very simple. I give you a node P. I imagine its subtree. Remember, that's P and all the descendants after it, including the leaves. And I just simply ask, okay, well, what's the height of that subtree? What is the height? Remember, that's the maximum depth of the subtree rooted at P. So what we're going to do is we're going to augment our data structure, so our binary search tree, to include an attribute that is going to be the height of the node. So this is going to be the literal height. Now, in some practical applications or some other implementations, you're going to see you can sometimes get rid of the redundancy of this height by including so-called balance factors. So the height could be like 1, 0, or -1. I'm not going to do that here. I'm just going to compute the actual height of the tree. So I'll leave those kind of optimizations to you, but we're not going to worry so much about that. What we'll give works perfectly fine. So the big thing I want you to take from this is that whenever I create a node, I'm going to assume its height is 0. And note that if it's an internal node, its height has to be 1. But note that as we're going to be seeing later, as we perform our operations, this height will get updated to be 1 correctly. So I'm going to assume that we have access to two methods called getHeight and setHeight for a given node, so I can access the height and modify it. So just to give you a clear idea of what I mean, so imagine I have this binary search tree here. I'm not going to write down the keys in this tree, but I want you to I just want to illustrate this idea. So each one of these nodes is going to store its height. By the way, what's the height of this tree? How would you compute that? Remember, I gave you a general algorithm for a tree, for how to compute the height. How did I do that? Well, let me just do it again. So imagine each one of the leaf nodes has height 0, which it does. This has height 0. Oh, don't forget the leaf nodes on this one. These all have height 0, right? So what's the height of this node? Well, it's the maximum of the height of its children, by our definition, plus 1, right? So the height of this node is 1. The height of that node must be 1. What's the height of this one? Well, it's the maximum, again, of the left subtree's height and the right subtree's height plus 1, right? So this height would be 2. The height would be 1 here. And what's the height of this node? Well, it's the maximum of the height of this node and that node plus 1, right? So the height would be 3. And this checks out just fine. Look how many edges exist for this depth node. So from leaf to root, I have 1, 2, 3. So the number of ancestors is 3. This child checks out. So what we're going to do is we're going to augment the binary search tree so that each one of these nodes will have in it an attribute that is actually the height of the node. Okay? So how are we going to do this? we're going to have an algorithm, and I swear this is going to be one of the easiest algorithms in this entire course, is if I maintain the heights of the nodes, so if I have this height attribute in my nodes, how can I compute the heights? Do I have to compute it over the entire tree like I did previously? No. Remember, the tree actually has the heights stored in their nodes, so all I have to do is compute that directly by using them, right? So I'm going to give you an algorithm here. It's called recomputeHeight. It takes in a node, it updates the height of the P, which is the node. And I'm going to just to make a slight assumption here, because this algorithm is always going to be run on an internal node. The way it's going to work is that you're just going to apply set height for P. So I'm writing this in Java-like pseudocode here. So I have 1 plus the maximum. Remember, this is our definition of what the height of a tree is. So this would be the tree rooted at P. So I just get the left child and I ask what its height is. Then I get the right child and I get its height and I compare those, pick the larger of the two, and then I add 1 to it, okay? So that's all this is. It's really simple. How long does this take? Now, if I didn't know what the heights were of the nodes, this would take how long? Well, it would depend naturally on how many nodes I have in the tree, right? But we want to stay away from that, right? The whole idea here is that we have these stored, so this is only going to take constant time. Remember, I have an attribute called height. This is in there. I don't have to go recursively going through the entire tree, right? So here I can just compute this quite nicely, and it's just in constant time. And this only introduces a constant amount of space into each one of the nodes. So I just introduce an extra space of big old 1. So really, this isn't too hefty of a penalty. Now, the big idea I want to give you here is that we're going to try to maintain the heights of each one of the nodes in our tree so that we don't ever have to recompute the height of the entire tree or any one given subtree in my tree. Does everybody see that? So as long as I can maintain the height of each node P in my tree, I never have to actually go and recompute them across the entire tree, which would be an expensive step, right? I would have to do it for all the nodes, which isn't a good thing. I want to just maintain the heights. Does everybody see that? So that's going to be the big goal with this. And if I have that information, I should know if it's so-called height balance, which I'm going to define next. So let me define the height balance property. So the height balance property is as follows. For every internal node P, the heights of its children differ by at most 1. So what do I mean by this? So imagine I give you some node P. So here's P. I consider the left subtree, so which would be the node rooted at its left child, and the node rooted at its right subchild. So imagine this is just my left child, and it has height h sub L, or h of L, or HL. The context, as long as you can clearly see that, it's just HL and HR. So I'm going to have, this is going to be the height of this subtree, and this is going to be the height of that subtree. All I'm really saying is that if that is the height of the left subtree and the height of the right subtree is at most 1 for every node. I hear the crickets again. For every node. I mean literal crickets. I'm not talking about you. Don't worry. Hopefully we're having a good time here. There's literally a cricket over there. It's staring at me. Yeah. Anyways. So this is the height balance property. So what we're going to do, and our goal is to maintain this height balance property. So what is an AVL tree then? What's an AVL tree? And it's quite simple. I'll give you the definition of an AVL tree now. What's an AVL tree? An AVL tree is as follows. It's a binary search tree that satisfies the height balance property. So, if it satisfies the height balance property, we call it AVL. So, an AVL tree must satisfy this property. So our goal with our data structure is we're going to make sure it always follows this property. So every time we make a modification to the tree, it must satisfy this property. That's our goal. So we're going to maintain this property like we've done with our previous data structure. So this is going to be a very common theme, and this is a very common thing you do in algorithms, is you try to maintain so-called some invariant. And as long as that invariant holds, you can get the nice perks and properties that would come with that. Oftentimes it comes following from some property that object has. So now, with this definition, I'm going to prove the following claim for you. So the claim is that the height of an AVL tree is at most the following. It is at most 2 log base 2 of n plus 2. So that's the claim. So we're going to try to prove this, and if this is true, that means that the AVL tree has height big O of log n, meaning it's height balanced. Does everybody see that? So let's prove this. So what I'm going to say is let H be the height of an AVL tree T So it's worth noting that I'm proving this for any AVL tree. So when you read a statement like that, you should read for an arbitrary AVL tree T. So I'm not just cherry picking a particular example. It has to be true for all of them. So what do we know about a binary search tree? It's a proper binary tree, right? T is a proper binary tree. So I'm going to invoke this property. This is why it's convenient to have this. So there's a nice property that we actually know, and this is one of the ones I pointed out at some point and said, this is a rather interesting and important property. It was like the last one I gave you. So that the height is actually less than or equal to the number of internal nodes. So what we're going to do is we're going to use this relationship to help us determine the height of the AVL tree. So if I come up with something that derives the number of nodes in the tree, and if I find some way of relating this with that, then we're done, okay? That's going to be our game plan. So here we go. So I'm going to define n of h, let n of h be the minimum number of internal nodes in T of height h. So I'm asking about the number of internal nodes. So I have n of h, where h is the parameter I feed n, and h is the height. So the idea here is that I'm going to try to find a minimum number of internal nodes so I can make this as small as I possibly can on this side. Okay? So what does n of h mean? So let me draw a picture. We're going to try to figure out the relationship of n of h. So let's first talk about n of 0. What would a tree that has height 0 look like? Well, it would just look like this, right? It would just be one of those leaf nodes that just has no data, it has no records. So this is when we have h is 0, right? So that means n of 0 is just, what is it? How many internal nodes are here? There's none, right? That's just a leaf node. Remember, we're counting the number of internal nodes. So we got 0 here. How about n of 1? Okay, so now this is interesting. So remember, we have to maintain the height balance property. So what's the smallest number of internal nodes I need to create a tree with height 1 that is AVL? Well, here's one idea, and I think this is the optimal one, is, okay, well, the heights of these nodes are 0. The height here is 1, right? You'd agree with me that this is the smallest number of nodes that I could use to create a tree of height 1, right? How many internal nodes are here? Just 1, right? Okay, how about n of 2? What's n of 2? Well, remember, we have to maintain the height balance property. Here's a suggestion I have. What we're going to do is I'm going to take, now remember, I need to make sure that the heights don't differ by more than 1. So I'm going to take one of the sides to be a leaf node, and then I'm going to maybe do this. You'd agree with me that the heights of these nodes here, those are 0. These are 0 here. The height of this one is 1. But the height here is 0, right? But that's okay, right? Because it only differs by at most 1. So if this is 0 and that's 1, it differs by at most 1, so we're okay. And the height here is 2. Notice that you can't do any better than this, right? Suppose I did only have 1. Do you see how that just won't work? Okay, so how many nodes do I have here? How many internal nodes? I have 2. Okay, now this is where it's going to get a little bit interesting. Okay, how about if I have a height 3? What can I do? Well, I'll give you an idea. Let's think about this. Look at like my 2 previous cases, kind of like blueprints. I know that I can create a tree with a minimum number of internal nodes of height 1, that's AVL, right here, right? It's right there. Here's one with height 2, right? Maybe if I put those together, maybe I can create one with a minimum number of nodes with height 3. So here's a node, the left child here. Maybe what I'll do is I'll put that one I have over there, over here. Then I'll put the one I had for n of 2 right here. So you'd agree that these ones have height 0. This says height 1. This says height 2. However, this one has height 1, right? That has height 0, height 1, and they differ by at most 1, right? So height here is 3. So what can we say here? So what's n of 3? Can you do any better than this by any way? Can you see any better way of doing this? Can you do it with 3 internal nodes? So if I put a leaf node right here, what would happen? That would mean the height would become 0 for that left subtree, which would differ by more than 1, which isn't good, right? That means it's not AVL anymore. However, if I put an internal node here, that gives it so that the height is 1. How about if I do it on this side? Is there any way I can somehow branch another node? No, it's a binary search tree, right? So it's going to either have to fork some way regardless. It may look a little different than this tree, but I like this tree. So you might come up with an alternative one, but you cannot do better than 4. So n of 3 is 4. Do you see a general pattern here by any odd chance? Okay, let's do n of 4. Let's do n of 4. Okay, what's n of 4? Well, I'm going to use the same idea. Okay, I know how to create an AVL tree with height 4. what can I do? I just take this one and I combine it with that one and I put a node that is the parent of these two subroots these would be its children. So I just take a node, and on the left I'm just going to draw the one I had for n of 2. So it just looks like this. Why am I doing this? It's because, remember, this one has height 2. And remember, I wouldn't want to use 2 subtrees that are n of 3, right? That would introduce more nodes that are internal nodes, right? But I already established that these are the smallest ones that I can possibly use, right? That's why I'm using them. They might look a little different. Like, you can probably posit other versions of the same tree, but the point is that's the minimum number of nodes. So the shape isn't really... See, I could always permute some of the ways that I arrange the tree. However, the number of minimum nodes is going to end up being the same. Does everybody see that? So all I'm doing is I'm using these as building plans to create other trees. So the point here is that the left subtree of this node, this one right here, that's just going to be one I had for n of 2. This is the one for n of 3. So what's n of 4 then? Well, what's n of 4 then? Well, look at it. Okay, this is n of 2. That's n of 3, right? And then I add 1 because I introduced an internal node. Does everybody see that? So in particular, I'll write this in a little bit of a different way. I'll say n of 3 plus n of 2 plus 1. Which is what? What is that? That is, n of 2 is 2, n of 3 is 4, so this would be 4 plus 2 plus 1, which is equal to 7, right? Does everybody see the pattern yet? So if I gave you a general formula for n of h, what would it look like? Thus, so you can actually prove this using a concept called mathematical induction, but I won't do that here. I hope that the pattern seems clear enough for you. That n of h is equal to n of h minus 2 plus n of h minus 1 plus 1, right? Actually, oh my, yeah, let's leave it like that. So that's going to be what n of h is. Is that neat? So I have my base cases here. So given any one of these, I can build larger trees. Does everybody see that? So what am I going to do? I want to make an observation here. What does this function look like? It's a recurrence relation, but regardless, it's still a function. What does this look like? If I were to plot out the result of n of h, what does it look like? Does the shape of the function look like this? Does it look like this? Does it look more like this? Which one does it look like? If I were to look at each one of these results, I'll give you a hint. There's this plus 1 here, always. Does this get any smaller at any point? No. Does this get any smaller at any point? No. So it does not look like this. It does not look like this. It looks more like this. What kind of function is that? This is called an increasing function. In particular, it's a strictly increasing function. So it isn't even just that it's increasing, it is strictly increasing. So there's none of these humps anywhere. It's just going to be always getting bigger. So we're going to use this property of this function. It's a strictly increasing function. So we're going to use that property. So n of h is a strictly increasing function on h. So, what can I say about this? So, n of h minus 1 must be strictly bigger than n of h minus 2. That's the big property I'm using here. And we have the following. So, now I have this relationship. So, this comes from the fact that n of h is strictly increasing on n of h. So, the strict part means it's a strict inequality. Okay? So, I'm going to use this to come up with a nice relationship between n of h and h. So I have this property at my disposal. So here's the one I'm going to use. So what's n of h? What's n of h? Well, it's n of h minus 2 plus n of h minus 1 plus 1, right? Well, I can rewrite this using this property right here. So what I'm going to do is I'm going to imagine if I have, okay, I have n of h minus 2. N of h minus 2 is obviously smaller than n of h minus 1, right? But it's most definitely going to be the case that if I take these two terms, lump them together, but treat them as n of h minus 2, I get this. I get this relationship because it's strictly increasing. So I can just ignore the plus 1. I don't really care about that. The point is that it's a strictly increasing function. And I have two recursive parts to this recurrence, and I'm just going to write each one as the smaller of the two. Does everybody see that? So I'm just going to rewrite n of h minus 1 as n of h minus 2, and I'm just going to discard the 1 because it doesn't do anything for this inequality. I only just care about the fact that it's a strictly increasing function. Okay? Does everybody see that? So I'm going to use this. This is a very important step. So what is n of h minus 2? Well, it's going to be equal to, actually, sorry, let's make it so I'm going to use this. It's greater than or equal to 2 times n of h minus 3 plus n of h minus 4, right? So all I'm going to do is I'm going to expand out what this is. And I'm just going to ignore the plus 1 again, because I don't really care about that. So technically this would be a strict inequality, but I'm not going to worry so much. Then, what can I do with this? What is this? Well, each one of these I can write as 2 of the n of h minus 4s, right? So you would agree with me that this is going to end up being equal to 2 times 2. Actually, it's not equal to. In fact, it's strictly less than 2 times n of h minus 4, which this is, of course, equal to 4 times n of h minus 4. I'm going to repeat this pattern over and over again. Does everybody see I can do that? So I'm just going to do the exact same thing. I'm just going to expand out what this term is. And I realize, hey, look, it's only just 2 times. It can be bounded by 2 times that whatever the lower term was, because it's strictly increasing. I'm going to do the same thing again. So this is going to be, this is greater than 8 times n of h minus 6, all the way down to it being, at some point, you're going to eventually get to some point where we have 2 to the I of n of h minus 2i. So at some given step, notice that every time this goes up by a multiple of 2. So if I just keep doing this by some power 2, because these keep going up by powers of 2, if I give you some arbitrary I, it's going to be related to 2 times I. Does everybody see that? So it's going up by multiples of 2 here, but each time here it's going up by a power of 2. It's going down by multiples of 2, it's going up by powers of 2 in the multiplicative factor. So this gives me a nice inequality. Does everybody see that? That is, n of h is strictly bigger than 2 to the I times n of h minus 2I for any integer I. Such that what? Such that h minus 2I is greater or equal to what? I want to make sure that's at least 1 so that I can play around with this a little bit. Okay, so I'm just going to assume that I want to make sure it's not too small. So what I'm going to do is I'm going to pick I such that h minus 2I is either 1 or 2. Because we know how to compute those, right? So this is the so-called magic number I'm going to select. So I'm going to pick I to be the ceiling of h over 2 minus 1. So remember, I'm taking h over 2 and I'm rounding it up. Minus 1. Then, for h is greater or equal to 3, what are we going to have? What are we going to have? I'm just going to put in that I, and then the following. So I know n of h has to be strictly greater than the following. 2. So what would I do? I'm just going to put in I, and it's going to be right here. So that's what I is going to be, and I'm just going to put that in. So 2 to the what? It's 2 to the h over 2 with a ceiling, minus 1, times n of h minus 2 times the ceiling. I'm getting ahead of myself. The ceiling of h over 2 plus 2. I'm just multiplying out that extra 2 because it's 2 times that, so I'm just saving myself a step here. Which, if I found this is just 2 to the power of h over 2 ceiling minus 1 of n of 1. You would agree with me that it's either going to be 1 or 2, right? If I put in this particular I. If not, just double check it. So you would agree with me that if I just put n of 1 here, it's either going to be n of 1 or n of 2. So I'm just going to put n of 1 and I can guarantee this in this relationship. But what is that? What is that? This has to be greater than or equal to the following. Well, what's n of 1 again? Do you remember what n of 1 was? N of 1 was 1. So remember, this is 1. But what is this greater than or equal to then? So what's greater than or equal to this? What I'm going to do is I'm just going to get rid of the ceiling because the ceiling will just round up this part of the exponent. So I can just write this as 2 to the power of h over 2 minus 1 without the ceiling. Because putting the ceiling there only makes it bigger. So now all I'm going to do is I'm going to take logarithms of both sides. Of both sides to obtain. So I'm just going to do log base 2 of n of h is strictly bigger than. Now, if I put a logarithm, log base 2 on this, it'll be log base 2 of 2 to the power of h over 2 minus 1 on the exponent here. So I can use the power rule of logarithms to pull that the h over 2 minus 1 in front. So I end up with h over 2 minus 1. Remember, log base 2 of 2 is 1. That's where log went. Therefore, we can say the following. Therefore, h, because now remember, I have h right here. There's h. That's the game plan, right? I wanted to get h related to n of h. So what I'm going to do is I'm going to write this in terms of h. So I'm going to multiply by 2. And then I'm going to just add 1 to both sides. Therefore, h is less than 2 times the log base 2 of n of h plus 2. But what's bigger than n of h? Well, I know this is going to be less than or equal to the following. 2 times log base 2 of n, right? There clearly cannot be more nodes than, the internal nodes can never be more than the total number of nodes in the tree, right? So this is totally valid because n of h is less than or equal to n plus 2. And we're done. Therefore, the height of a height balance, this is indeed a height balanced tree because the height is now big O of log n. So we see that because it has a constant there, constant there. So a constant just sitting in front of the log. So I'll let you think of how this would be big O of log n. So where are we going to go from here? So now I have the mathematical machinery here that's saying, hey, look, this is actually going to end up being a height balanced tree. So I know for certain that the height is going to be big O of log n, as long as it's an AVL tree. As long as we make sure it always stays an AVL tree, we're good. So we're going to talk about rebalancing, right? Remember I told you that the idea was in the self-balancing trees that we make modifications to the tree. We're going to need to potentially rebalance the tree. So we're going to start talking about this. So we're going to talk about rebalancing AVL trees. So I'm just going to remark that AVL trees inherit. So I mean literally in the sense that you might think of inherit the operations of a binary search tree. So I'm just going to assume that this already has access to all those methods that we did the other couple of classes. The AVL tree will rebalance on what kind of operations? What are the only operations that mutate the tree or change the tree? Will rebalance the tree. The AVL tree will rebalance the tree on what kind of operations? What are the only ones that mutate the tree? Put and remove. So if a put happens or a remove happens, we'll maybe have to do some rebalancing. So the goal when we do this is we're going to imagine, like what we did when we computed the heights at each one of the nodes, we imagine it trying to we imagine the tree being balanced bottom up. So from an internal node that is the smallest subtree in that tree, we're going to work our way up to the root, and we're going to perform rebalancing operations from the smallest possible subtree. So wherever it occurs, it's going to be from the smallest one. So to rebalance. So to rebalance the tree, we will always rebalance the smallest, and it's all in air quotes, you see, in the smallest unbalanced subtree. So wherever the unbalance occurs, we're going to look at always the one that's the smallest unbalanced subtree. That means we're going to work our way bottom up as we make modifications. So the idea behind how we're going to do this is based on the concept of a rotation. So the idea that we're going to have is we're going to use a so-called simple rotation. So I'll usually refer to this as rotate. So what we're going to do is, as we make modifications to the tree, we're going to try to, in order to maintain those heights of the nodes, like I said previously, we're going to do some manipulations to try to perform so-called rotations. Now, let me draw a picture and then I'm going to kind of illustrate the idea. So we're going to rearrange the nodes so that we can maintain the heights. Just want to get it just right. I don't promise these pictures are symmetric. So the idea of a simple rotation is as follows. So now I don't claim that these are imbalanced or anything. I'm just illustrating you the idea here. So imagine an imbalance occurred at X here. So the way I want you to imagine this is, imagine I have something like this. Imagine I have this hanger here. I have this hanger. And imagine I have X over here, and say it's imbalanced. So it's a lot heavier on this side. So imagine there's like a string that's attached to it strings along the hanger over to the other side. So if you know anything about pulleys, what you try to do is you try to pull this so that you can either level it or pull it up like this. So what we're going to do with our simple rotation is this, basically. So if ever it becomes a little bit imbalanced, meaning that it's going to violate the height balance property, because if it gets too bad, you want to imagine it's like playing the floor is lava or something. You don't want to touch the lava, okay? So what we're going to do is we're going to try to promote X to be the new, it's going to move this up like this, just like my hanger. I'm going to pull the string. I'm going to pull that string so that I can get T1 away from the lava, okay? Because we don't want to burn our friends that are in T1. So what this is called, so I'm going to perform a right, I believe I call it a right rotate. So this would be what I call rotate X. So I'm going to apply rotate on X. So rotating on X will promote X to become the parent up here, and this will demote Y to become the child of X. So now X used to be the parent, a child of Y. Now Y is now a child of X. So by doing this, I can get T1 away from the lava. Now, I can't necessarily guarantee that every time I do this on an arbitrary node, that it's going to cause this one to stay away from the lava, but in the way we're going to use this, it will. Okay? So there's right rotate, which will promote X to become the root of this subtree. Likewise, it might be possible that Y might be the one that's really close to might be starting to be imbalanced, and T3 might be really close to the lava. So I don't want the T3 to touch the lava, right? So what I would do is I would perform what is called a left rotate, this would be rotate on Y. So this is all rotate on Y. What this would do is promote Y to become the root of this subtree and demote X down to be the child. Does everybody see that? So just think of it like this. So think of my hanger, and I am just pulling along the string like this so that I can balance the tree. So this is going to be the primary mechanism for which we're going to use to rebalance the tree. So if I find that one of these sides is going to start really tipping a little too close to this lava, I'm going to pull it away by imagining I pull the string I pull the string down this way so I can promote up X, just like if I was pulling that string. Keep it away. Think of it like a big, I'm just trying to use the pulley, okay? So that's the idea. So that is a simple rotation or my rotate. So you're going to find I'm going to draw a lot of pictures here because the great thing about doing this is that all I'm doing is modifying references to nodes. I'm not doing a whole lot of crazy things beyond that. So rotations shift around. They shift around the heights by rearranging nodes, while maintaining the order of the tree's elements. Okay, one thing I did not talk about that you probably caught on between my two pictures is it isn't quite really just that I pull it like a little pulley here. What other thing happens? So remember I said you got to think about it kind of like it's getting heavier if it really is lopsided like this. So what would you do? Imagine your pulley had weights on one side. What would you do to help pull it over towards the other side? You would pull the weight off of one side and put it onto the other side. That's what T2 is. So all I'm going to do is I'm going to trade T2 with this left subtree now to be with the right subtree. Because when I promote X, it no longer really has this right child anymore. This right child now has to go somewhere else. It goes with the right subtree on the rotate. But this is the biggest part. This is the part I did not talk much about. Is it's maintaining the order of the tree's elements. If I read this off as an in-order traversal, what would it look like? Well, I visit all my children in the left. So this would be T1. Then I would visit X. And then I would visit my right, T2. Then I would visit Y. And then I would visit all the nodes in T3, right? That's what the in-order traversal should do. And remember, we have to still maintain the binary search tree property. That's why these rotations need to do this. In contrast, this one, if I read it from an in-order traversal standpoint, what should it look like? It should look like T1, X, then I go to the right, go left, T2, Y, T3. Notice it does not change the order. Does everybody see that? So notice this operation, this rotate operation, does not change the ordering of the nodes. So all we have to do is try to make sure that we don't manipulate this incorrectly. You'll find very much when you're doing these rotate operations or rotations, the more broader ones we're going to talk about, it's very easy to lose nodes. So the way I like to compare this to is like manipulating a linked list on steroids, because now you have parents, children, and the fact they switch from left to right sometimes. So just be very careful if you're implementing something like this. So our main rotations are going to be based on these here. So there are two kinds of rotations. Single rotations, and double rotations. You'll find out why I called them those things. Single rotations and double rotations. So there's going to be 2 of each of these. So 4 in total. They're going to account for all 4 possibilities that could happen. So when we come back, I'll talk about these rotations that in their core, they're really just using this simple rotation idea, or rotate. It's going to apply these rotate operations. Okay, so when we come back, we'll look into that. and we'll have some more fun with AVL trees. So I say thank you very much, and have yourself a beautiful day.